Hello, I'm Connor Party, and I'm here to present integrating single unit and pattern codes in DCNN's train for face identification. My co-authors are Yvette Colon, Matthew Hill, Carlos Castillo, and Alice O'Toole. Modern deep convolutional neural networks are state-of-the-art in machine face recognition and can identify faces across substantial variability. However, despite their invariant performance, the output from a DCNN retains information that is considered tangential to the task of face identification. This could include information about gender, viewpoint, illumination, or more. Here, we ask what type of a visual code a DCNN might possess that would allow it to represent multiple sources of information simultaneously. To do this, we analyze the properties of single-unit responses from units at the top layer of the DCNN, as well as the full ensemble of these top-layer units in conjunction. So first, some introduction. We start with low-level vision, where early visual features are well-defined and semantically interpretable. They resemble Gabor filters and function as edge or location detectors. These early visual features are considered synonymous with neural receptive fields. In high-level vision, the goal of the visual system is no longer to encode an image, but rather to decode what is in the image. Therefore, the representations are categorical, image invariant, and relatively non-retinotopic. Receptive field interpretation is more challenging. This could be why researchers have struggled to find semantically meaningful labels for neurons in the inferotemporal cortex. A neuron can be face selective, but what does this actually mean? Historically, face recognition algorithms mimicked the approach of low-level vision. In older models, images could only be compared if they showed faces in almost exactly the same viewpoint or with the same illumination. Modern DCNNs achieve high identification accuracy even when comparing wildly different images. This resembles the type of representation seen in the primate IT cortex. To understand the representations that emerge from the top layer of a DCNN, and hopefully by analogy IT neurons, researchers have considered two approaches. First, single-unit analysis has been used for image-based visualization of DCNN receptive fields. Unfortunately, this assumes semantically interpretable and retinotopic DCNN features. Second is the analysis of population code responses. In one such study, Hill et al. Plotted the face space from a face identification network for images that varied in viewpoint and illumination in a highly controlled fashion. The results showed that the face space was organized hierarchically, such that identities were clustered within gender groups, illumination was clustered within identity, and viewpoint was organized within illumination. Both the single unit and the ensemble perspectives are interesting, but developing a full understanding of how faces are represented requires the simultaneous analysis of both. Here, we analyze the juxtaposition of single unit and ensemble codes for a DCNN representation of identity, gender, and viewpoint. We will show that these attributes separate in the ensemble code, but are confounded in single units. So now we move into the methods and results. Here, we address the following specific questions. For single units from the DCNN, how many units are necessary for face identification, gender classification, or viewpoint prediction? Further, how predictive are the individual units? For the ensemble code, are there directions that correspond to identity, gender, or viewpoint? And then finally, we ask how the single unit and ensemble codes relate to each other. So we start by focusing on the number of units necessary for each prediction task. To test this, we randomly selected sets of n units from the top layer of the network. Samples were selected in powers of 2 from 2 units to 256 units, and 50 samples were selected for each sample size. In effect, this meant taking the face image descriptor that would typically be used to identify faces or classify gender or viewpoint, and keeping only 2, or only 4, or only 8 units or any other sample size at random. We used a ResNet 101-based DCNN trained for face identification using over 6 million images. This produces a 512-dimensional descriptor vector for each image at its output. We tested the network using in-the-wild images of over 3,500 identities. Each image in the test set was processed through the network to obtain the full dimensional output. Output vectors were compared to measure the similarity of two face images for identification, or used as input into linear regression models to predict gender or viewpoint. Using the full descriptor, identification accuracy measured by area under the ROC curve was nearly perfect. Gender classification accuracy was 91%, and viewpoint could be predicted to within about 7 degrees of error. Using the unit sampling procedure just described, we get this result. Sample size is plotted along the x-axis, and identification accuracy is plotted along the y-axis. Using all 512 units as noted, identification accuracy is nearly perfect. Sampling down to only 16 units still yields near-peak identification. In fact, accuracy is still high with as few as 4 units and still well above chance with only 2 units. So the fact that faces can be accurately identified with so few units and that the units can be selected at random introduces two possibilities. First, perhaps each unit carries the same redundant information as any other. Then we would expect the response vectors from any given 2 units to be strongly correlated. Alternatively, if the identity cues in each unit are diverse, there should be only a weak correlation between individual units. What we see is this. This is a histogram of the correlations between all possible pairs of units. Overall, 95% of the correlations fall below an absolute value of 0.17. This indicates that individual units possess unique, diverse cues to identity, not redundant cues coded repeatedly. So accurate identification is possible with very few randomly selected units. But how many units are needed for gender classification or viewpoint prediction? Here, the stories are a little bit different. Using all units, gender classification is very accurate. However, with fewer than half of the units, gender classification starts to decline rapidly, reaching near-chance performance with 16 units. Viewpoint prediction accuracy falls off even more steeply, requiring nearly all of the units in order to make accurate predictions. So these last few graphs show us a couple of interesting things. First, there are multiple types of codes that seem to exist within the same set of units. Second, the code for identity does not behave like either a sparse code or a distributed code. The units here seem to do something different. We weren't expecting this, so we stepped back and asked what makes a good unit. Historically, we think of an identity unit as something that fires whenever it sees someone particular. But, defined more carefully, a unit is useful for identification if it can separate images of different identities across the length of its vector, while simultaneously managing to cluster together images of the same identity. Or in other words, a good unit would have a high ratio of between identity spread to within identity spread. The same can be said for different levels of gender or viewpoint. How do we measure between class variance to within class variance? We can use the ANOVA. Using ANOVA, we can compute an F ratio for each individual unit and use the respective effect sizes as an index of each unit's quality. For each attribute, we performed an ANOVA for each of the 512 units. The independent variable was either identity, gender, or viewpoint, and the dependent variable was the unit's response. The resulting effect sizes act as an index of the attribute separating capacity for each unit. For identity, we get this. Each item along the x-axis is a single unit, and the effect size is measured along the y-axis in r². Each unit possesses roughly the same amount of identity information as any other. In addition, the ANOVA is statistically significant for every unit, and the effect sizes are large. Then we measure the effect sizes of each unit for gender and viewpoint separation, shown here. These effect sizes are extremely small compared to identity. But if we zoom in, we see that the pattern of effect sizes reflects the pattern that we saw for identity. Most units here are somewhat interchangeable. Further, over 70% of the effect sizes for gender are statistically significant, as are over half of the effect sizes for viewpoint. So next, we move on from unit-based codes and instead consider directions in the representational space formed by the network. Here we ask, in the full representational space, are there directions that correspond to identity, gender, or viewpoint? We applied principal component analysis to our original unit response matrix to re-express the face image descriptors in terms of principal components. We then repeat our ANOVAs on these re-expressed face image descriptors, such that the point of analysis is no longer a single unit, but is instead a principal component. So previously in the unit space, we saw the graphs on the left. On the right, we see the effect sizes in the principal component space. These show strong differentiation by identity, gender, and viewpoint. Identity information dominates in the early principal components. Gender information is strong both in the early principal components and about halfway through the PCs. And viewpoint dominates after the gender information fades away. But given that some of these effect sizes are so small, do these regions matter? As it turns out, they do. We measured prediction accuracy for identity, gender, and viewpoint using a sliding window of 30 principal components at a time. Identification accuracy was highest using the early principal components, which contain the most identity information. Gender and viewpoint prediction were most accurate using the principal components that contain the most gender or viewpoint information, respectively. So finally, how can we look at the relationship between the single unit and ensemble codes? Given that specific principal components carry information about specific attributes, We can measure the amount each PC contributes to a single unit to determine whether DCNN units prefer or are tuned to specific attributes. To do this, we compute the angular similarity between each PC and each single unit. For example, if a unit is tuned to gender, we expect a high similarity between that unit and the gender-informative principal components. In fact, what we see is a completely homogeneous similarity structure across all the principal components for identity, gender, and viewpoint. One example unit is shown here, but in fact this is true for all 512 units in the network. There's almost no difference for any unit in the relative proportion of identity, gender, or viewpoint components that make up that unit. So finally, in summary, the results here present a novel type of representation that combines multiple variably distributed codes within the same set of neural units. This suggests a new type of representational code that could inform theories of high-level visual processing. As an example, we can imagine what a neurophysiologist might encounter if examining these units. First, since identity modulates the response of individual units so saliently, each unit would appear identity-tuned. But rather than being identity-tuned, each unit actually spreads identity information across its entire range of potential responses. In addition, since gender and viewpoint is so weak within each unit, no units would appear gender or viewpoint tuned. So, the distributed codes for gender and viewpoint would likely not be detected, even though the ensemble of units allows for very accurate gender and viewpoint estimation. We believe that neural units may not signal semantically interpretable features, but should be seen simply as organizational directions in the representational space. Therefore, if DCNN-like representations exist in high-level visual cortex, neural tuning functions will not be informative about the high-level visual code. So that's all I have. I want to say thank you to my co-authors and to my lab mates. And if you're interested in further details about the work presented here, then I want to point you towards a preprint copy of our paper on arXiv, available from the link and the QR code displayed on the screen. Thanks again, and I look forward to hearing from you.